So good afternoon for everyone, and possibly good morning to you. Thank you for taking the time to join us. I can see a lot of people have already joined the webinar today, so thank you for your attendance. We normally have a little bit of time. We give a few minutes for people like me who are running from meeting to meeting these days to join in good time before we start today, so there may be a few more coming. Please note that we will be running a little panel discussion here with some of our team and some guests, Stuart from GE, but also I should let you know that this is part of an ongoing series of webinars that we conduct. If you are able to join us today live, that's wonderful. If you're not, don't worry, because we record these sessions and we offer access after the event to a YouTube link recording it for people who weren't able to make it even though they registered. And of course, if you've got any questions or it raises any concerns or inquiries, we'll be happy to handle those after the meeting. Now, during these events, typically we'll share our screen. You can hear us and see us talking and chatting about these subjects. We've got some interactive polls to check some of your views and opinions on these applications, but the chat is not enabled in this version of Zoom, but our Q&A channel is open. Given the nature of these discussions, it's difficult for us to talk about these things and host all of the Q&A live, but we'll capture all the questions and answers. And if we can't address it and I can't guide Stephen and Stuart to them, then we'll try our best to answer and follow up with people individually afterwards. That's typically the best way to do it. So with that in mind, we wanted to say hello and welcome to Stephen Blair, who's Head of Power Systems Engineering at Synaptec, John, who's also in charge of our business development for HV Power Grids, and a special guest, Stuart Clark from GE, who's a specialist in wide area management, which of course is the subject matter of our session today. So if I just push on a couple of slides, of course, it would be crazy if I then didn't do a quick introduction about who we are and how we fit into the scheme of things before we get to the meat of this. So for those of you who don't know, Synaptec have been in the market for about 6 years now, developing a unique technology which is used in transmission because we found a way to deploy networks of distributed electrical sensors. And these are unique because we figured out how to measure fundamentally current and voltage completely passively. And these passive networks of sensors are all connected together through optical fiber, which typically exists in HV systems, which gives us long range, high accuracy, and instantaneous visibility of multiple locations. And at each of those locations, of course, you no longer need civil works and buildings, power supplies, data network, telecommunications, GPS clocks, and all of the equipment that's traditionally associated with powered instrumentation. So this is a smaller footprint with less equipment, a lot greener, certainly more locations and faster way to get a lot of data brought back centrally to give you better visibility and control of the network. So yes, it reduces the capital cost of instrumentation, and it radically reduces the cost of networking sensors together, which is a major headache for wide area management systems like PMU measurement and state estimation. But it enables new operational cost savings as well, because we can see not only more locations, we are operating a lot faster and gathering more data and better insights in remote and inaccessible locations. So as a business, we've come from transmission, but we're also involved in offshore wind. We're also getting involved in railways because fundamentally they're all very complicated and distributed power systems that we want to help to avoid or reduce outage costs and just outages at all, and do so by getting more sensors in more locations, generating better data for better decision making. So that's us and our business in a nutshell. And just real quick on the next slide, I wanted to give everyone a quick overview of what we do. So today we're focusing in the sort of bottom center of this crazy map that says we have this one powered and network device called our interrogator, which is typically rack mounted in a substation. connects only by optical fiber, which is already pre-existing in the network, so it can reach very long distances and see a lot of locations, either a high density of sensors in trials like digital substations where we can instrument multiple bays, or in renewable offshore wind where we're looking at lots of cables and lots of terminations and lots of power quality injections from different turbines. But generally speaking, we're very well suited to wide area monitoring because we're able to offer things like continuous point on wave interrogation and data sampling from a lot more locations without the need to backhaul that data through some kind of switched IP data network. We're avoiding a lot of the traditional architecture involved in IP switch networking, PDCs and sort of data concentrator stages to get data back centrally to make better decisions. It's particularly useful, of course, because in these remote locations, you don't need a lot of the power and communications infrastructure that used to be necessary to bring these signals back. So multiple things that we do for multiple different reasons across the domains of protection, automation, control, and asset management. But today, we wanted to introduce some conversation themes that Stephen and Stuart and I want to have a chat with you all about, which is really focused on that first aspect of wide area visibility and control and what these new technologies could bring you additionally above and beyond the sort of traditional methodologies that we associate with phaser measurement. So Stephen, it's over to you, and then I'll get some polls ready when you want.
Okay, great. Thanks, Al. I think actually to get things warmed up, we're actually going to start with a poll. Just to find out from the audience what their thoughts are. So this should now be available for voting right now. So really, we're trying to find out what are the really key barriers, I mean, that we can think of that prevent greater kind of monitoring of power systems over a wide area. Is it the capital equipment cost of the PMUs themselves and the sensors, or is it actually the substation and installation costs that are dominant, or is it the wide area networking, IT infrastructure, or another crucial point is it actually somebody who takes ownership of the data and is interested and enthusiastic about analyzing it and processing the data? So there's quite a lot of votes coming in, and okay, so I think you've ended the poll there, Sal. So everybody should be able to see the results. Actually, I think that's a surprising result, that equipment cost seems to be popular. That the IT infrastructure is also one of the top choices here. So that's quite interesting. Okay, so I think with that in mind, we'll come back to some of these topics in a moment, I'm sure. But I just wanted to kind of do a bit of sort of scene setting. So I'm sure the audience will be pleased to hear there will not be much PowerPoint in this presentation. We're going to try and keep it to discussion, and in particular, Stuart, who's joined us from GE. Stuart and his team are kind of the sort of go-to experts for sort of wide area grid stability. So I think Stuart will have a lot of interesting experiences to share as well. So, but to kick things off, I just wanted to start off with maybe a couple of deliberately provocative slides. So I'm sure most people in the audience will remember and be familiar with the event a couple of years ago in August, where there was a complicated series of events involving lightning strikes, which tripped protection in the transmission system. And in parallel with that, there was some oscillation activity, and eventually a Hornsea wind farm tripped. And then there's other complications that sort of cascaded on top of that, with different sort of tranches of distributed generation tripped because they're installed with different protection policies. You know, there's some on vector shift, whereas some are on loss of mains, and then there's I think there's still two different sets of loss of mains settings. Some are on the old settings. So this has resulted in quite a complicated behavior, and ultimately, to save the wider system, about 10% of the GB system had to be tripped off. So it's over 1 million customers, but the system did recover. It made the headlines, and there were some very unpopular results from that in terms of transportation and so on. But the system did survive. And then at the bottom half of the slide here, there's actually Hornsey happened to trip again. I don't mean to pick on Hornsey here. It's just something that I picked out from some ESO slides from late last year. And actually there were a couple of trips, and also a trip of the sort of the Western Link, HVDC link on that kind of goes down the west coast from Scotland down to sort of Deeside. So the point I'm trying to make here is that these events are complicated, and they're happening sort of relatively regularly. The more recent events weren't as serious because I think in particular the rock-off relays that were not tripped, and that helped. But so far the ESO in GB has been doing a pretty good job of keeping the system stable. But their job is becoming increasingly difficult just with the increased presence of converter and connected generation, and the loss, the reduction in inertia in the system, the increase of HVDC interconnectors, and so on. So these are all quite fundamental challenges that are really, really difficult to address. So again, here I just wanted to raise some questions. Again, these are deliberately provocative and open-ended and quite difficult to answer. But I wanted to, across the panel, to sort of maybe we can sort of give an impression of some of our experiences here. So to pick one of these to kick us off. So I've already mentioned the impact of distributed generation and distributed energy resources. They can have a knock-on impact during these major frequency events on the grid, and they can be really quite difficult to account for those because it's difficult to quantify. It's sort of hidden in the lower parts of the system. And also, I already mentioned about the impact of oscillations, and we'll actually come back to that later on, I think. So I think that's probably enough of me speaking. Is there anything, Stuart, yourself, you would like to pick out on here? I don't know, maybe like some of your work on inertia measurement and forecasting, or any other area that you wanted to?
Yeah. Thanks, Stephen. Picking one of the questions there, the location of frequency measurements, does it matter? And this links into the other topics of inertia and impact on events of distributed generation. So we're seeing, as you mentioned, distributed generation can be disconnecting during frequency disturbances due to either to vector shift or to high rate of change of frequency. Two different measures trying to essentially catch the same kind of thing, the rapid variation in system frequency that's intended to be indicative of a collapse of the system, but in reality, with our grids getting lighter and lighter, we're seeing such disruptions in the frequency occur more easily during normal disturbances, during the frequency decline, as happened in August 2019, and that can cause large numbers of distributed generation to disconnect, making a bad disturbance worse. And as the system is getting lighter, as inertia is reducing, and the system is behaving more and more as a collection of interconnected centers of inertia, frequency behavior varies across the system. Rate of change of frequency behavior varies across the system. So measuring frequency, monitoring frequency across the network becomes much more important to understand what the behavior of your grid is during disturbances, and what the different centers of inertia are, what each of their inertias are, and monitoring and being aware of how rock-off will behave at a regional level when you have a big disturbance on your grid. That's becoming more important.
Yeah, thanks, sure. Yeah, totally agree. Having the locality does matter, and having a wide range of inputs across a wide area, I think, is key. So I think we'll probably come back, touch on some of these topics later, but in the meantime, we have another poll. So if you can launch that, so this one is about some of the more the pain points with actually using wide area monitoring, assuming it's it's available. And we just wanted to get a feel from the audience about your opinions about what issues you've experienced. So it might range from no issues. If anyone selects that, then I probably don't believe you. Or another problem that I think everyone experiences is it's difficult to filter out bad data. Another common issue is the quantity of data. The large numbers of terabytes per year that the PMUs can generate. And the fourth point here is that it's difficult to actually find value in the PMU data, just partly because of the vastness of it. But it's perhaps not obvious how to really use that and get something that's actionable in the control room. So we have a good number of responses now. Okay, let's hold on. And well, there are some superstars here who have no issues using PMU data, wide area monitoring data. So that is good to hear that things are improving. But clearly, there's evidence here across the board of some of the issues that we've identified, and there's probably some others that we haven't thought of here. That the majority of participants here are sharing some of the pain that that we all experience when using wide area monitoring data. So with that, I just wanted to very briefly highlight something that Saul mentioned earlier in the intro, which is about this concept of continuous point and wave monitoring, which is a slightly confusing term, to be honest, but it really just means looking at the waveform data like you get from a digital fault recorder or from a protection relays event record, that sort of thing. But I just wanted to clearly highlight why that's useful and why that's different. So at the top right of the slide, we're looking at PMU data, which gives you a new phaser, perhaps every 20 milliseconds or maybe a bit faster. And on the bottom right, we're looking at the actual waveform data that's underlying the PMU outputs. And it's quite obvious that the PMU data doesn't really show anything here, partly because we're looking at the positive sequence magnitude. But when you look at the waveform, there's clearly a profound change in the operation of the system. Obviously, this is an artificial scenario that I've generated in a simulation, but the same applies in real events where there's real complex events that you can only pick out from the waveform. So, transient oscillations and that kind of thing. You might still be on the fence about why that's useful, but I want to give like a really interesting example. So this was actually from a NASP event, North American Synchrophaser Initiative, which has a wealth of great information online that is really useful to look at. By coincidence, myself and Stuart were both presenting at this event last week. And there was a good presentation from Dominion Energy, which is a utility in Virginia in USA. And what they found from looking at their PMU data initially was that there was a strange interharmonic at about 8 Hertz that popped up in the system. And that was kind of suspicious. And then they eventually hit them that this was very consistently happening between sunrise and sunset. And of course, when they matched that up to other monitoring data, then it was quite obvious that it was due to PV. So whenever PV was connected to the system and generating, that's when this particular disturbance happened. What's also interesting is, well, first of all, they've witnessed this across many locations and at many different substations. So it was widespread throughout their grid, and it was interesting that they sometimes saw it in both voltage and current, or sometimes only in the voltage. So that's sort of information that can maybe help to actually pinpoint where the locations that are causing this event, which is really what you want to get to. And then finally, what they looked at was actually point on wave data, where they looked at the waveform, in this case, 960 hertz sample rate data. And what that revealed was that the oscillation mode was not at 8 hertz. That was kind of a red herring that the PMU data was showing. The real oscillation was at about 22 hertz. So it gave them, the PMU data was still useful to actually highlight the issue, but they had to do deeper investigation with continuous point wave data to really isolate what was going on, and then to work out the impact on the grid. So that's just due to the design of PMUs, that they intentionally block out certain frequencies, and you need the waveform to do true oscillation analysis. Before I move on, is there anything you would like to add to that, Stuart? Anything about your work on oscillation?
Yeah, thanks, Stephen. Yeah, we've seen similar to this example from Dominion. We've seen similar behaviour in other places in the world, including in the UK, in work we did on the Visor project with Scottish Power SSE, National Grid. We see these kind of high frequency oscillations. I say high frequency, particularly in the subsynchronous range, so anywhere above the kind of 2 hertz where the electromechanical behavior ends, up to 46 hertz or just below the synchronous frequency. There's more and more power electronic equipment going onto the grid, throwing out these kind of oscillations. And a few things, and these oscillations can simply be a quality problem on the grid, or they can have interactions with other power electronic oscillations with generator turbine shaft torsional mode. So you can end up with resonance, which can be very bad for the plant involved, or you can end up with interaction with resonance circuits created by capacitors and inductors in the network. So these oscillations exist on the grid already. As we're having more power electronics going onto the grid, they're appearing more and more and more. We've seen in this presentation alone, we've seen a couple of examples, and there's plenty more examples out there. So having the penetration of measurements is important to catch these, or certainly, if not to catch them, to track them down to where they're coming from. And one aspect of having power electronic driven plants such as wind farms is that you don't have one big generator to monitor. You've got lots of individual turbines, compensation plants, and so on to track the issue down to. And that's where the more monitoring, the better. But also I would reinforce the point about point on wave data versus PMU data. PMU data is not designed to catch oscillations at this higher frequency. Depending on the PMU filtering and the rate your PMU data is reported at, you can see that something is going on at a higher frequency sometimes, as in this example, but not all the PMUs will, depending on the model, the manufacturer, the settings of the PMU. You might see a completely different picture of the same oscillation in one device than another. And you really want the higher rate information as well. So point on wave is the best way to get a clean picture of this high frequency behavior, an accurate picture for proper analysis, and you need the higher rate. We were using data at 200 hertz in the Visor project, but other higher rates are good as well to see the oscillations in the first place. So more monitoring, because we have more power electronic plant. These things are happening more often, so we need more monitoring. And the point on wave point is important to see the proper oscillation, not what you may or may not see in the PMU data. Certainly once you know a problem, you know you've got a problem or you're worried about a problem, you need to be going down the point on wave route to know about it properly.
Yeah, thanks, Stuart. And I think that actually leads on perfectly to the next poll question. So, so at this time, we've sort of set the scene and explained what we mean by continuous point wave. You know, it's effectively like having networked digital fault recorders, DFRs. Where does the audience stand really on the best approach for wide area monitoring? It is what's done at the moment with PMUs over a wide area. Is that sufficient? Or do we need more PMUs? Or do we need, as myself and Stuart we're sort of just arguing, is there a real benefit from from having a greater expanding capability for waveform monitoring throughout the grid. Perhaps, not just waveform monitoring, but synchronized, permanent, long-term visibility of the real detail of what the system is doing. So thank you again for humoring us with participating in our polls. But yeah, there's a clear shift. It sounds like that Stuart's argument was very good there for defending more waveform-based monitoring, but the audience seems to agree that would be useful, and I think it's something that's not really missing. Sorry, it's something that is missing, but there's an opportunity now to really provide much greater visibility, including continuous point and wave. So,
for what it's worth, there, just picking up on Stuart's point from my perspective, we have our feet conveniently in two camps here. We do work with transmission, but also in offshore wind generation, and we're working with developers like Vattenfall right now on putting more distributed but critically permanent and synchronous power quality monitoring in these wind farms, because of course these effects coming onto the grid may be seen, as with your Dominion slides, in a kind of aggregate form at the grid connection, but even that isn't good enough, because you've got to go beyond that connection to each individual inverter and say, okay, where's the source of this problem actually coming from? Because it could be a specific turbine or a specific set of electromechanical problems that are occurring out there. So getting that granular detail and being able to trace back the issue to its source is very important, because otherwise you're only looking at an aggregated view of the grid connection from what is effectively 10 to 130 generator points. So I think it's critical to do both of these things. Everyone would love more affordable visibility that's dependable and reliable and fast, but you also need that greater detail and better sampling rates to be able to get the underlying issues identified and not the aliased kind of high level presentation seen. Yeah, definitely. Wind farm, it brings together so many important aspects that deserve quite considerable amount of monitoring. As you said, you have generators that are all multiple generators relatively close together on the same network, that their converter interface, so that they must be injecting harmonics. So there's likely sooner or later there might be a resonance issue in the network, because obviously the wind is intermittent, so certain generators may be out of service, so the network impedances will shift over time. Particularly if there's an HVDC link back to the shore, if the export cable is HVDC, then that wind farm is effectively its own little AC network, which has to be controlled. So there's lots of interesting things going on in wind farms, and that's why we think this continuous point wave monitoring is particularly applicable there. So
I have a question for Stuart there, and that is, in your experience, Stuart, as there is obviously a global shift towards digitization within the networks, do you see CPOW as basically that's the way we have to go? We need more data to assess the impact the equipment has, particularly mechanical equipment, on digitization and the networks as we bring them more up to date?
Yes, I think PMU data, particularly from the system operation point of view, if you're sitting in a grid control room, PMU data is the big thing that you're interested in to help run the grid real time and to analyze essentially to be the next evolution from the EMS world. So EMS is SCADA, it's only giving you magnitudes that every 1 or 2 seconds they're unsynchronized. PMU is giving you phasor measurements, magnitude and angle, they're synchronized. They're what you're really trying to get to with a state estimator to feed into your stability studies to know the real state of your system. So they're going to stay important, but particularly with all the power electronics coming onto the system and these higher frequency oscillatory behaviors in particular, as well as the other transient behavior, continuous pointer and wave is is important now and is going to become more and more important in more and more grids. What form that takes, exactly how we fit it in, whether we're doing things like streaming, I think in the immediate term anyway, I think it's unlikely we'll be streaming all continuous point and wave measurements to a central location. But what we may well be doing is streaming continuous point and wave from key locations, as we did in the UK already under Visor, to a central location to monitor, for the control room to monitor the state of the grid, know if they have any problems in their system. But then for things like analysing behaviour during faults, or analysing or doing individual monitoring of plants, so to work out exactly what turbine is misbehaving or how individual turbines are monitoring, you're maybe going to have local buffering or local capture by the network, by the plant owner, who will then ship some data on demand or continuously to the central location. So I think you're going to need both. PMU data is definitely important and handles a lot of the control room cases, but continuous point and wave becoming more and more critical because of these high frequency oscillation behaviors in particular.
Thank you, Stuart.
Yeah, thank you both. Good question. So I think next up is to hand over to you again, Stuart. Thank you.
Yep, thanks, Stephen. This was just really a slide that we put together to really just to illustrate the areas, and it's not an exhaustive list by any stretch, the areas in which, when we talk about WAMPAC, wide area monitoring, protection and control, what areas we can be covering. And the critical thing really is these two axes. You've got on the y-axis the rows, system performance. That's probably entry level for most utilities with the WAMs. They're primarily interested in getting data to look at, to find out how their plant is performing, to retrospectively analyze a disturbance, maybe do some model validation and identify issues as part of desktop study. And then the next level down, you've got operational awareness, where maybe just for your operational analysts in the back room, or maybe in your control room as well, depending on what level of adoption you're at, you're using WAMS data in real time to monitor and manage your grid. And again, going back to the UK, we had examples where we were using the oscillation monitoring that we had with point and wave data, using that to monitor the grid as new power electronic plant was being commissioned onto it, just to make sure that there was no big change, no worrying patterns emerged when we flicked the switch and connected the wind farm or the DC link or whatever it was. So operational awareness of things like oscillations, disturbances in the grid, and all sorts of other metrics that give you an idea of how the system is operating. And then finally, in that third row, you've got control, where you're taking the human out of the loop and you're actually using, you're taking full advantage of the speed, the accuracy, the synchronized nature of wide area measurements to identify a problem, quantify it, evaluate it, work out what the response should be, and trigger the response. So trigger a fast response, the correct response in the right place of the grid to deal with your disturbance. So that could be frequency response. You lose a generator in the UK somewhere, you want to bring up your response in the right place. If you bring the response up in the wrong place, you could end up destabilizing the grid. And there's lots of other use cases as well to do with things like having DC links behaving as AC lines in certain situations you might want. Quickly detecting, going back to the oscillatory stability example that Stephen had about Hornsea Wind Farm, when an event like that happens, you have sudden growing oscillation or a sudden oscillation in your grid, detecting that oscillation within a few cycles, triggering a response such as a change in control mode on the converter to mitigate the problem. So that's just some scope for what WAMPAC applications are, and they can vary across the security and disturbances area, dynamic stability, oscillations, system strength, and network and constraints, where you're mainly interested about the capacity and the performance of your system. And that's all really I wanted to go into detail on this slide. I think people can read it for themselves and maybe use it as some food for thought.
Yeah, thanks, Stuart. I think it's worth pointing out that this is not just theoretical. These are things that you've applied in practice, like the bottom left-hand corner, the wide area control. You know, you've tried that in the UK, and it's like business as usual in Iceland, I believe. Is that right?
Exactly. Yes, that's a good point. Thanks. I think everything on this slide is has been deployed operationally somewhere in the world, so it's not blue sky by any means.
Thanks very much, Stuart. So next up, you might be relieved to hear this is the final poll question. This time it's again related to the using PMU data, actually getting something out of it. And the poll here question is, and like with some of the other questions, you can select as many of these as you think applies. But what are the main data quality issues that typically occur or that you might have experience with when looking at PMUs? So some of the ones that I think we've definitely all experienced is data's missing, and that could be maybe a device has failed, or usually it's a communications issue. Time synchronization, that's a common one to occur. Even if the devices are perfectly synchronized initially, the clock might lose a GPS signal, for example, or similar issues. And sometimes we have to work with data that just has no time synchronization, and that can be really, there's a lot of labor involved in actually processing that and salvaging as much data as possible. There could just be straight up spurious data that you don't trust. You look at it and you're not entirely sure if it's correct or not. It might be correct, but it's not trustworthy. And then the fourth option, just to explain that one, is even when everything is working perfectly, the answer that's coming out of your PMU, it might not be, even if everything is as designed, the Rockoff measurement might simply be noisy just because of the nature of it. And also there's other side effects of PMUs, such as whenever there's a genuine phase step in the system, which might be completely benign, that can affect your frequency measurement. There could be a little blip in the frequency measurement. So when you have lots of complicated, complex events happening at the same time or nearly at the same time, it can be difficult to really process everything. So thank you all for voting while I was rambling about all the different options. And we have a clear winner on this particular poll question. Missing data or communications issues is really leading. Everybody voted for that, but then we're seeing some other people have obviously voted for the other aspects as well, in particular the measurement side effects, which is interesting to hear. So I think that's all we have in terms of slides and everything. Across the panel, are there any other aspects of wide area monitoring that is worth mentioning?
I've got a question, perhaps on behalf of some of the voters there, because you put up a thing, and I'll just share those results again, because this prompted a question for me, Stephen and Stuart, which maybe you can speak to. Now, from a commercial perspective, right, because I'm the commercial guy at Synaptec, we're talking to customers who say, okay, PMU measurement in and of itself is fine. Actually, the challenge is that, there's a lot of PMU enabled devices and relays out there on the network that aren't even networked and connected, because either we've got an issue with the cost of networking itself, which can be 100-fold more expensive, or at least 50-fold more expensive than the actual PMU device, or I think this vote here is talking perhaps about some of the other issues that I've heard people speaking about from the Visor project. So Stuart, I'd be interested to hear about this without sort of like pouring cold water on what happened in Visor too much, but what are the limitations and challenges of things like variable latency and bandwidth issues from these remote locations? Because these wind farms that we're talking about are not in convenient, well communicated and well networked locations very often. So is that one of the key challenges? It's the issue about the variability of latency, if not bandwidth.
Yeah, so I guess so like you say, bandwidth is one thing. It's usually manageable, but the variable latency it really comes down to when you're, and I think this was one of the things we actually touched on in one of the papers we did on Visor, was that when you're using a WAMS in anger and you have a large number of measurements pouring through your WAMS, you really need to know your real-time data streaming how to configure it and tune it properly. So if you think about it in a WAMS, if you have 100 PMUs in your system, every one of those PMUs will send you a data packet every 20 milliseconds, and the job of the phaser data concentrator, whether that's a first hop in as an intermediate regional data concentrator, or it's the final destination at your control room, it's got to receive all of those packets for each 20 millisecond sample, receive all of those packets, align them, combine them into a single time slice, and pass them on to any consumers or any historians or wherever that data is going to go. So things like latency, buffering, if you're combining multiple streams, having those streams tuned so that maybe most of the fast PMUs are grouped generally in one stream, the PMUs that maybe have much poorer comms behavior or longer latencies are in another stream. Basically, knowing your C37 data stream and configuring it properly can be important to make sure you get consistent, reliable performance from it. So these are all manageable issues, but you can't necessarily, if you don't have the large amount of bandwidth and high performance network headroom available, you need to make sure when you're setting up a large WAMS you actually tune it properly, and you can get reliable performance out of it. And that's like I said, something we went through in Visa, because it was the first time we were deploying an operational WAMS in the UK as an innovation project. But you can read more about that kind of topic in I think it's the most recent 2018 Seagrey paper we published, talks about data streaming there. Latency is, for monitoring, generally manageable. It's not unusual for a monitoring system to have latencies, say, in the 5 to 10 second region. It's not that your control room application will be waiting impatiently for data to arrive within 100 milliseconds. That's fine. For control applications, you do want the data to arrive quickly, depending on your application. If you're talking about fast frequency response, like we had in the EFCC project, you definitely want your data to arrive within a certain window of time. And that's when things like making the choice of TCP over UDP for data transmission can be important. Setting your data windows carefully so that you wait as long as you're comfortable with for data to arrive, but not too long that it becomes useless for the control application. And having graceful degradation in your control schemes. So being able to handle the situation where only 50% of your measurements arrive on time. That's having that kind of intelligence built into your control scheme or your monitoring application design becomes more important when things like latency and bandwidth are a concern. Does that, you can also, as a final comment, you can have intermediate PDCs deployed either at the substation or intermediately in covering a region, for example, and they can be doing something as simple as combining the individual PMU streams from multiple PMUs in a substation or multiple substations into a single stream, which has a huge impact on bandwidth efficiency. So a single PMU monitoring 3-phase volts, 3-phase amps, about half of the bandwidth from that PMU is just overheads, TCP or UDP headers, the C37 timestamp, all these other things. The actual measurement information that changes is only about 50% of that packet. So data concentrators, again, can be useful in reducing the bandwidth required, converting between TCP and UDP or other protocols for security or for reliability reasons, and also acting as a junction in your network to help the smooth flow of data streams. Does that answer your question?
Absolutely. Thank you. I just bringing it up because I thought it was worth teasing some more conversation out of, what's lumped together in that popular response there. There's a lot under the heading of comms issues that could be, people have very different experiences and of these issues. And I just thought it was worth teasing those out. As a last question, which maybe is one for you, Stephen. So, the work that both of you have contributed to, that NASP are leading in the US, it would be useful maybe to take a couple of minutes at the end here now and just try to explain why a higher frequency of sampling and publishing rate is actually beneficial. So you talked about catching transients and details, but how much more is good, and what's the level we've got to reach to provide sufficiency of insight and understanding?
Yeah, I think there's several different applications that continuous point and wave opens up. I think we touched on a couple of them, such as detecting oscillations at particular frequencies that you can't otherwise see properly through PMU measurements. So that's one of them. Another one, which is quite interesting, I think, is just being able to monitor when transients happen. So it could be any particular asset, like a circuit breaker or a CT might fail in the substation. If you've got continuous monitoring of that, and perhaps with maybe it just needs to be a couple of weeks kind of rolling log of that data, then when that equipment fails, then you can always look back at the data and analyze what happened. Maybe there'll be evidence of arcing that you could see in the waveform data, and that would give you a bit of intelligence about how that asset failed, and then how you could learn from that and prevent it happening in future assets, or put the monitoring in place to be able to detect early signs of that degradation over time. So I think it has a real role in condition monitoring and asset health. And then the other big thing I think is just for assessing harmonics in the system, which obviously has applications in the grid and has, I think, very, very compelling uses in offshore wind, as we discussed earlier. Resonances can pop up quite readily, I think, in an offshore wind system, and particularly where you've got lots of generators closely coupled, injecting harmonics. There's particular risk there for harmonics being an issue, and really you need this continuous point and wave kind of level of visibility to really tackle that. I think also in relation to your earlier question, Saul, there are actually a lot of point and wave monitoring devices out there, with digital fault recorders and protection relays, but the issue is that they're not networked, and probably the utilities have no intention of networking them because they're there for protection. And a lot of clients that we've spoken to, they don't want to mix up these two things, monitoring and protection. They want the protection to be kind of siloed and safe and as secure as possible. So that's why it's not really able to be unlocked at the moment, even though the functionality is technically there for both PMU and continuous point and wave. So I think our proposition from Synaptec is really that we can much more easily provide dispersed measurements without the conventional kind of overheads and costs and civil infrastructure and that sort of thing. But we bring the data back at a high quality and high sampling rate, a minimum of 4 kilohertz or higher for other applications, and we enable that to be accessed. The point about the data bandwidth is also quite important here, because obviously continuous point and wave has even more data to manage and stream. So if PMU streams are challenging, then continuous point and wave might sound insurmountable. But there are techniques that can be applied, and we've been looking at this about how to compress the data, losslessly compress the data, so you don't lose any information, but you can make much better use of the existing infrastructure. So for example, it's possible to compress about 10 three-phase data streams, which could be voltages or currents, down to into about 1 megabit per second of data. So there's quite a lot of opportunities there. So it's not something to completely rule out. It does need bandwidth, but it is feasible. And as Stuart mentioned earlier, there's trade-offs you can do by not sending all of the continuous point and wave monitoring data everywhere or centrally, but maybe there's something that can be done locally within at substation level or regional level, or perhaps there's key data streams that go to a central location for certain applications. So hopefully that answered that question, Saul.
Brilliantly, you covered it, and that's really helpful. So Just keeping an eye on the clock here on behalf of everyone in the audience, it's probably time to stop there. And first of all, say thank you to everyone for coming along and listening to us. Especially thanks to Stuart from GE for joining us on the panel today. Much appreciated to have the expert opinions contributing to the conversation. Please remember, everybody, that this is one of a series of webinars. So we have previous ones from the past and more coming up every month where we're tackling sort of critical application themes. If you've missed them out before, the recordings of them are available. You just need to get in touch with me or Stephen or John and we can help you out. Additionally, anyone who registered for this event and those of you who attended today, we are recording this and we'll put a link up to a private YouTube channel, typically 1 or 2 days after the event so that you can review them. And then of course, if you've got specific other questions, I think we tackled all of the ones that are available here today live, but if there were others that then were prompted, please do get in touch with us because we love a challenge. And we're always happy to hear about issues that we possibly could be able to help with. So, just remains to say thanks very much everyone for your time, much appreciated, and we hope to speak to you further on this subject very soon. Thanks and goodbye.